Thank you very much for providing me this opportunity to. So most of my life I was giving these talks about computer science with help of Samson's ideas, and now I got a chance to maybe give a talk about what I've known of Samson with the help of some computer science ideas. So I will stay away from most of my paper, which contains some formulas, and actually, you know, we'll try to not give a real talk about the results further than what's useful for a talk. I think we should maybe sometimes talk about ourselves. So here is how I'll tell you I think maybe three parts. How I met Samson, and then I'll ask a second question, and in the end I'll have a claim. So how I met Samson. Before I met Samson, so this is not the picture of how I first saw Samson, but it looked something like this. I mean, when I saw him, it was 1991, and he didn't have Apple computer with him, certainly, but it was the Category Theory 1991, the global category theory event, where I'm sure Prakash was present as well. And Samson was the invited plenary speaker, and I knew so little about computer science that I don't think I understood much of his talk. But when he finished, then Saunders MacLean stood up, and I probably didn't understand enough mathematics either, because I don't remember what Saunders MacLean said, but he was speaking for a while. Yeah. And then André Joyal stood up, and André Joyal said that category theory has a very good opportunity to help with computer science. We should pay attention to hardware. It's important that we study hardware by category theory, said André Joyal, and then Bill Levere, I think, asked an actual question. And I came out of it with the idea that it felt like maybe computer science is presenting some sort of danger to category theory. Saunders MacLean at the time was certainly quite interested in class field theory. I knew by the people he was bringing there. And then 2 years later, after various aspects of my life collapsed, I got a job in computer science from Samson. And this is so Samson is the prominent person with white shirt. And I don't know, you surely don't see the list of people. In addition to myself, he was leading at the time, but it was a very large group, and everyone was in it. You know that John Reynolds was the visitor for a while, and it was an important group. And at that time, what I gathered from of course 40 people, there was a lot of work in all kinds of directions, but Samson was interested in interaction categories, and that was something that I thought I was not. I had a chance to understand. I knew that category theory was helping us with abstract structures, and interaction categories were sort of intended to. On one hand, there was this part of computer science where category theory was harvesting abstract structures from computation. That was the notational semantics, and it was sort of capturing the functional view of computation. And then Samson was pointing out that there was this entirely different part of computer science, of semantics of computation, which was, the way I understood it, of course, very roughly, it was something like lambda calculus, but not really about functions, but some other things, and that was process calculus. And so we were trying to to bring together not just the functional behaviors, not just the functions which computation was computing, but also maybe to capture the effects and to define frameworks where both the notational and process calculus view of computation could be expressed. And here Samson in this paper with Raja and Simon is contrasting the two approaches and proposing that the categorical structure, which consists of course of objects and morphisms and composition, should be used, not just used to capture process specifications as objects and processes as morphisms and interaction and as composition, but actually, if you look here, the other way around, we can interpret a category as the thing where the objects are giving us some sort of specifications and morphisms are capturing some sort of processes with or without effects, and composition is interaction. And after about 3 years, I finally understood how this worked, and I had a joint paper with Samson. It was so convincing that I think that's the only paper where Samson was reluctant to be the first author. But I sort of went and ran with the concept. And since I became a computer scientist, and before I became even a mathematician, I used to write programs. So then I went to Palo Alto with these specifications, with the idea of categories which consisted of specifications. And already a year later, we started building a tool basically. So, I mean, I don't know to which extent these categories of specifications that we use there were my misinterpretation of the idea of categories consisting of specifications that Samson was telling me about for a couple of years. But even if it was a misunderstanding, it was a useful misunderstanding. So in contrast with in Samson's interaction category specifications were kind of constraining the behaviors by specifying a set of traces or a set of allowable moves or something. And in these categories that we were implementing, a specification was rather a predicate which was constraining which traces would be allowed. So it looked something like this, and a specification. It consisted of some basic specification, and every state, stats were state descriptions, was an extension of these of the specification, which was prescribing what was allowable in all of the system. And then these state descriptions were satisfied at one state, and at another state, some other state description would be satisfied, and then the state transition between the two of them would be an interpretation of one theory in the other, in a sense that the transition from A to B would be the interpretation of theory of A in theory of B, not unlike the rule for assignment in homology. And we then the upshot of that was that you could compose them. You could calculate co-limits of these things, and you could compose. So then, co-limits of specifications would be giving you kind of concepts underlying several specifications, and while you were computing this co-limit, you could compute the limit of the underlying state machines, which would be executing all that all programs were doing, and it was kind of giving you an alibi to do category theory and get funding to build tools. So the idea was kind of slightly different. Objects were still specifications, albeit specified as logical theories rather than sets of traces. Then morphisms as processes. Processes were trimmed down to transitions, so that the pattern of morphisms was giving you a state machine, and then by calculating limits and co-limits, we were composing things. And that went on for a number of years, and in the end we built some tool which has been used. Okay, so it's Samson's birthday, and I should not be talking about my own work, but I just wanted to tell about, you know, how this one idea, which it took me some trouble to understand, how it suggested an answer to a question which I was asking myself from the beginning. Originally, you know, one answer to this question, as we all know from the textbooks from which we learn category theory, is that categories are good for working mathematicians, or, you know, some people boast that it's general abstract nonsense, lovingly, of course. And the message of my experience as I was slowly learning computer science from Samson was that categories were actually good as concrete abstract nonsense, as not just abstract structure, but concrete categories which you build to interpret these things, also for computer scientists. But so the message which I want to give you is not a claim like this. They say that we actually should, well, albeit at least for children, for people's birthdays, we should give them questions and not answers. So the question which I wanted to ask back is, are also, does the opposite hold as well? And maybe that, at least, you know, from the point of view of these guys at the World Conference of Category Theory 1991, this might be a question which deserves maybe more consideration. So let me try to argue in that direction. So here's a real category theory problem, going really, really far back. Look, Springer Lecture Notes in Mathematics, volume 1924. 24. Going back to I'm jumping ahead to my next sentence, in which I say, capturing Jim Lambeck's lectures from not 24 but 1966 in Zurich, and he talks about completions of categories, and he works out all kinds of completions, most of them arising from Yoneda embedding, and the central open question remaining after the book is that whether there exists, so sup and inf are co-limits and limits. Whether there are, we would say, complete and co-complete, so whether someone gives you a category A, and you want to have a complete and co-complete category such that the category from which you started is dense under limits and co-limits under this embedding. So in other words, someone gives you a category and it has some limits and co-limits already in it, and you want to embed it into a category which has all limits and co-limits, but to preserve the ones which you have had. And it's a natural thing to ask at the first sight, in analogy to the Dedekind completion of an ordered set, he says. But on a second thought, it becomes dubious. So let's see what exactly is the question. So, was this Dedekind completion of a partial order? So Dedekind constructs, as we all remember from maybe high school, real numbers from rational numbers. He starts from rational numbers and then embeds rational numbers into lower intervals, into lower sets, and on one hand, and on the other hand into upper sets, and then he maps each lower set into the set of all of its upper bounds, and each it should be upside down. Each upper set into the set of its lower bounds, and then this on both of these lattices, this induces a closure operator, and in all of them you extract the cuts, Dedekind cuts, which we know as one definition of real numbers. And McNeil then generalizes that. You can do that with any partially ordered set. You take on one hand the complete lattice of lower sets, on the other hand complete lattice of the upper sets. the fact that one is joint completion and the other is meet completion gives you the adjunction. So you can map every lower set into the upper set of its upper bounds and the other way around. And you know, in each of them you've got the fixed points of these closure operators, and they give you the generalized notion of cuts. And what this amounts to is you start from this partially ordered set and you get a complete lattice where any meets and joins that may have existed in this partially ordered set are preserved under the inclusion. So what Lambeck asked for is to generalize this. You begin from a category, and Yoneda embedding into contravariant presheaves, gives you into contravariant representative functors, gives you the co-limit completion, into covariant representative functors gives you the limit completion, and again, because these two things are completions, you got these two functors, and you get an adjunction, and they're taking a tree sheaf or a contravariant functor into the co-limit of its total category, and the other way around. So the question is now, what can we find something like fixed points for this adjunction, or maybe algebras, or maybe Kleisli categories or something, which will give us this this bicompletion here, so that so of course A is generating under co-limits the contravariant functors, and under limits the covariant functors, and we would like it to generate under both limits and co-limits here. And we would like A, whatever we're reading this for, to have all limits and co-limits. So that was Lambeck's question. And a couple of years later, John Isbell wrote a paper, and he says Lambeck asked whether there's a category which satisfies all this, and it merits a study, and I propose to call it Lambeck extensions, and Z4 doesn't have a Lambeck extension. And then he provides a maximally obscure proof by he just takes Z4 times Z4 and counts how many morphisms are there, and there is not enough morphisms, so it can be complete. And so what does this mean? This is, so, you know, going back to the intuition. So we have specifications. So suppose the category consists of things we specify, and so the interpretations between our specifications are captured as morphisms, and then co-limit of these logical theories are giving us composite logical theories. And if we have some sort of behavior represented by these state machines of specifications underneath, limits will give us composite processes. And what this says is that if I have some concepts which I have captured by co-limits in this framework of specifications where I specify some of my knowledge and some of my implementations, then I cannot conservatively extend this thing, you know, by adding all the derivable concepts and while preserving all the concepts that I have specified. So for me, this fact has been scandalous for you know, the logical intuitions emerging from the world of specification. So really, Isbell's negative result appeared to be a mystery with as regards the specifications and the practice of using categories in this logical framework and for generating programs. I mean, that paper of ours was claiming automated software generation and so on, and we can't even conservatively extend our theories. So why can't we do this? And then I'd like to maybe work out the question a little bit. So what's the general form of this question? Let's forget about, or let's generalize beyond both sets and Lambek's question to enrich categories. So this V for posets would be a two-element lattice, and it would be set for ordinary categories. So we would like to join weighted limits and weighted co-limits while preserving those that exists. And the adjunction works exactly the same. And V, for instance, if it's positive real numbers, all of this is stated about metric spaces, and some of that is in that paper, in the paper which is in the proceedings. So now, if we generalize this and separate maybe specifications in one category and processes in the other category, because what we're really doing is, on one hand, we specify what we want our systems to do, and then we run them, and we observe these processes and maybe improve our specifications. And that gives us these matrices which capture both specifications and processes. And so now the question is slightly more general. So can we complete a matrix like this? So in ordinary category theory, it's some profunctor, and in posets it's a lower set in one poset, an upper set in the other poset. Can we now, what can we do with this adjunction now? And in general, in full generality, what we, and the special case of completing enriched categories follows from the fact that, you can treat a category is really just a square matrix. So here's what we know. Dedekind McNeil completion gives us enriched by completion which is enriched in a Boolean algebra with two elements, and V matrix by completion is the staple of concept analysis. And then we can work out both by completions, both category and matrix by completions. We can work them out as long as we are enriching our categories in posets. Everything works, and in the proceedings we have that for generalized metric spaces. But Isbell says that if we take the category over which we're enriching to be the category of sets and functions, then no. Then there is no by completion. There may be no by completion of a category. So here's a direction to maybe understand what is going on from the point of view of concrete abstract nonsense, or by looking at the intuition of categories of specifications and processes. So let's look at the categories which are enriched. So this category can be further from being a poset. And as Marcelo pointed out, this is the free category with byproducts over one generator. So it's the category which has natural numbers as objects, and it has matrices of natural numbers as morphisms, and we're looking at tensor as just the product of the numbers. And so n-enriched categories, you can think of it as a category, except that and it has Hom sets, but a morphism is not an element of the Hom set, but it's a bag from the Hom set. So it's a set of morphisms with multiplicities, and then you compose them by matrix composition. And we still have this same framework for by completion, except that now, since we have these byproducts, now these extensions, these two adjoint functors, become ordinary matrix composition. So, when we start doing this, we're not doing anything but linear algebra with natural numbers. So someone gives you a matrix of natural numbers here, and you would like you would like something like singular value decomposition of that matrix. That matrix will, of course, induce a linear operator one way, and the transpose will induce a linear operator the other way. And what you will do is you will compose them one way, and you will compose them the other way, and you will perform spectral decomposition. You will find eigenvalues, and lo and behold, the eigenspaces will play the role of these closed spaces, except that we don't have enough algebraic numbers here. So we continue to replace algebraic numbers in a certain way. So I'm not going to push with the answer to this side. I just wanted the point which I wanted to make is how actually it is useful to just, I think, start from concrete abstract nonsense intuitions and think of abstract categorical questions in terms of what things on two sides of a problem mean. And as soon as we start thinking of them as, maybe in this case separately, specifications and processes, immediately the intuitions in this case from linear algebra arise and point towards the solution. So I just wanted to maybe illustrate that the answer to the second question may be positive, and to finish with the claim that whatever categories might be good for at the end, I think one thing which is beyond doubt is that they're good for French. Thank you, Samson.
Well, comments or questions?
I guess what you were showing us was sort of illustrating how you could get a positive solution to the problem. And you see a way of connecting this back to the setting you were really interested in with object specifications, maybe in some enriched format. You didn't have time to talk about that, but I assume is that the sort of direction you're going, or is this, will the applications be a bit different?
Latent semantic analysis is the staple of all data mining, and it's done by singular value decomposition. And so whenever Netflix or Amazon recommends what you like on the basis of what you have liked before, they are performing this kind of analysis. Except that they're performing the shortcoming of that analysis is that it cannot learn. If we begin with a specification of what people like, before we capture their current ratings into what they like now, we need to throw away everything that we've known before. That's the unfortunate property of latent semantic analysis. So they're kind of the direction where it comes from is twofold. On one hand, what we were working with in evolving specifications and in protocol analysis was that we wanted to specify the current algorithmic knowledge about the protocol, and then as things are running or as new attacks take place, to be able to extend the existing theories which we have from before by this new knowledge added by the new matrices. So on one direction we were extending these specification frameworks that we specify ourselves. On the other hand, computation is not anymore just programming. Computation is not anymore just specifying what we want programs to do and then generating code and then observing software systems and updating the code. Computation is also getting some information which is completely undeclared and analyzing it, and both these things are done by analytic methods like this, which without our previous categorical structure don't have this capability to learn. They are, in a sense, machine learning is one part of network computation, and recommender systems and network analysis are another part. This kind of framework brings both of these together, and my claim is that on one hand, our semantics of programming and the paradigms that we're coming with from there are not just helpful but necessary to bring these things together. And on the other hand, it's also a natural extension of computer science that we've been doing.
Oh, let's thank the speaker again.